So we're asked to consider this sum, where, okay, for convenience, a is greater than 0. So the thing about this sum is that our f of n has an infinite number of singularities. So that means that when we use the standard formula for evaluating sums, so when we use this standard formula for evaluating a sum, f of z has infinitely many poles. So we're going to have another infinite sum. So we want to work out the sum we're trying to find, f of n, and we get another infinite sum. So how can that work? Well, it can occasionally work if somehow we can evaluate this second infinite sum. And this can happen if, by some chance, we actually know what the infinite sum is, which is normally not the case. Normally this ends up being more complicated than this one. But in some unusual cases, it turns out that this sum here is related to the sum we're trying to find. And then we can actually find out what f of n, the sum of f of n is. So in this example, we don't really expect to find this sum for all values of a. What we're aiming to do is actually just see if it's possible to find it for some values of a. Now, why don't we expect to find the sum? Well, basically, if you think about what happens when a goes to infinity. Now, coth is a function which tends to 1 for large argument. So if a gets very, very large, then basically we've got 1 over n cubed summed. And we already know that 1 over n cubed is some special function. So we can't really have any hope at all of finding a general answer to this for any a. But we're going to see what happens anyway and see if we can find a special value of a for which we can actually get a closed form solution expression for s. So first thing to notice is that coth is an odd function, n cubed is an odd function. So this is an even integrand. And it also has a pole at n equals 0. This s is related to this double sum in a simple way. This is an even function, so the negative terms, if we write f is equal to all of this, the n negative terms are the same as the n positive terms. So in the end, 2s is equal to precisely this sum. So we can write down straight away that 2s is equal to minus pi times. Okay, now we need to work out where the residues. Okay, well I'll just write it as this to start with. So 2s is equal to coth na over n cubed and minus infinity n not equal to 0 and going to infinity. Okay, so this is our f of n, and then we need to find out where the residues of this are. So obviously we've got the poles of this. So we've got poles at n equals 0. So zj is equal to 0. But also, where does this have poles? Well, coth has poles. Coth, remember, is 1 over tanh. And tanh has zeros at the same place as tan has zeros. So it's n except multiplied by pi. So basically, tanh has zeros at I na equals I m pi. So that means coth will have poles at those places. So I'm now writing everything in terms of z. So okay, za, f of z. So it's za equals I m pi. So I have poles at z equals I n pi over a. Which includes 0, but so we end up with, let's do the 0 ones separately. So we're going to have minus pi times the residue of, because that's a special this is not a simple pole, the others are simple poles. So we'll have the residue of coth z a cot pi z over z cubed at 0, and then we're going to have minus pi times the residue of same thing, but at zj, but now summed over all possible m, except, so m going from minus infinity, except m equals 0, which we've already dealt with in the first term. So that this is, so it's m not equal to 0 and m going up to infinity of zj equals I n pi over a. So this, let's actually work out what these residues are. So we've got a residue because of this, we've got a simple pole when m is not 0. Because of this, we've got cosh divided by shine. So the shine bit, when we do p over q dashed, will give us cosh. And we're differentiating, so we end up with an extra a. So I'm just going to work out the residue of this, so hopefully that's going to be clear. So just the residue of one particular m. So I'll get a factor of 1 over a coming from differentiating shine za with respect to z. But otherwise I'll get cosh divided by shine, which cancels. And then I'll get cot, and I just need to evaluate everything else at z equals I m pi a. So I get cot pi, then I've got another pi here, so that makes pi squared I m over a, and then that's all divided by z cubed, which is all of this cubed, so it's I m pi over a all cubed. So simplifying this, where it's the 1 over a cubed gives us a squared on the top, and we've got pi pi cubed on the bottom, and also n cubed. Now, when we do cot of this, cot of I times something, cot of course is cos over sine. Now, cos of I something just gives you cos of that thing, cosh of that thing, and sine of I something gives you I times shine. So we get an extra I on the bottom, which will give us I to the power 4, which is 1. So the I goes, And on the top we've got left with coth. So it's cosh divided by sine of the real thing. So it's coth of pi squared m over a on the top. Okay, so this sum here, we're meant to sum this thing here over all integers m apart from m equals 0. And we see, well, this is almost the same as the original problem, which so there's no way we can solve this, except for the fact that if we choose m right, then we get exactly the original problem. So how can we choose, if we choose a correctly, then we get exactly the original problem. So if we choose a equals pi, then what would happen? We would get coth pi m, the sum of coth pi m divided by m cubed. And if a is pi, that would mean that we get exactly the same sum that we're trying to work out. So the only way we can evaluate this is if we choose a to equal pi. So we now put a equals pi, and this is the problem we can actually solve. So if we put a equals pi, we can replace this sum of residues by, I'll just do everything properly. So we end up with a squared is now pi, so we end up with pi squared on the top times pi divided by pi cubed. So all this goes, and we just end up with coth of m pi over m cubed. So this thing here, now, sorry, I'm going to change this to a pi now. So this thing here, this now gets changed to a pi as well. This thing here is the same as this thing, except that I've got m instead of n. So all of this thing here is precisely 2s. So now we're almost done. We've got, I can move this over to this side, and we've got 4s equals minus pi times the residue of this thing, just evaluated at z equals 0. Okay, so we've got 4, I've added an a here, so it's clear. So 4s of pi, the only one we can possibly do, is equal to this. Now to evaluate, okay, so we know the easiest way to do this. So what have we actually got here? We've got a polar of order 5, okay, because this has a simple pole at z equals 0, this has a simple pole at z equals 0. So the easiest way to do this is to have a series. Now we have the series for cot. So cot of pi z is equal to 1 over pi z minus z cubed pi cubed over 45. We're probably going to need that term, but I think nothing higher than that. But we can use this to get the series for coth. If we instead consider cot iz is, as we just said, cosh z divided by I shine z. So therefore I times cot iz is equal to coth z. So to get the series for coth pi z, coth pi z is just I times cot I z. So we end up with just replace the z's by iz. And I've got I cubed here, so I'll just change that to a plus sign. Get I times and so on. So multiplying through by the I get rid of this I. This I gives me I squared, gives it a plus sign here. And this I gives me a minus sign. And multiply through. So that's the series for coth pi z. And all I need to do now is work out the residue of this. So just multiplying this by this and by z cubed, I need to work out what the coefficient of 1 over z is. So I'll get 1 over z. So obviously this z cubed is going to cancel this z cubed here for one of these. And then the other series is going to give me the 1 over z term. So I'm basically going to be looking at this. Okay, let's clear the board. Okay, so multiplying these two things together, multiplying the series together, what I'm looking for is a term which will give me a z squared. If I get the z squared term from here, when I multiply by 1 over z cubed, I'll get the residue. So how do I get z squared? Well, I can get it from multiplying this by this. So overall, that will give me sorry, this should have been this is minus. Sorry, this should be a minus as well. Okay, so this is the cot one. This is the cosh one. Okay, so how do I get a z squared? So from multiplying this term by this and this term by this, which both give coefficient of z squared of minus 1 over pi z times, okay, we don't want the z anymore, so it's pi cubed on the top and 45 on the bottom. So we end up with two of those. We get one from doing this times this and one from doing this times this. So that gives us a minus 2 pi squared over 45. But we can also get a z squared from this times this, which will give us a minus pi squared over 9. So multiplying top and bottom by 5, this ends up being minus 7 pi squared over 45. So the final answer is, for this, is minus pi times that. So that gives us 7 over pi cubed over 45. And the answer we want in the end is s of pi, which is 7 pi cubed over 4 times 45 is 2 times 90, which is 180. That's our final answer. So this is the only sum of this form that we can evaluate just when a is equal to pi.